All right, so today, guys, we start in on chapter 6, which is our first real jump into energy. And so chapter 6 is thermochemistry. Now, energy and chemistry is talked about in a number of different ways. But in order to really start the conversation on energy, what we really need to do is come up and look at some definitions. Okay? And so some definitions to look at are, you can see there's a whole list of these things. And so we're going to take a little bit of time and talk about what each of these are. You'll start to see some of these in use over the course of this chapter. So there are a lot of different definitions that we need to know. Okay. So first one, just energy in general. Okay. So energy is, as it's put here, the capacity to do work or produce heat. And we can think about the energy from a standpoint of, well, how we use it. We use it in a lot of different ways, right? We use energy, electrical energy a lot of the time. Electrical energy is using electrons moving through wires to do something, okay? And those electrons moving through wires have mass and they have velocity, and so they're moving from one place to another, and so they're doing work. So electrical energy does work, and there's a whole chapter on electrical energy later on, like a Chem 102 course, when you get to electrochemistry, but that's late in a Chem 102 course. What we're going to be more interested in is heat, okay? And we'll talk about those two things as we, move forward through this chapter, okay? One of the things that we really want to know is we need to know first and foremost as we start is the law of conservation of energy. So the law of conservation of energy is essentially the same as the first law of thermodynamics. So we've got these two things kind of listed together right here. Okay, and so basically what the law of conservation of energy says is that energy can be converted from one form to another, but it can't be created or destroyed. So in other words, when we do stuff in the world, sort of just like the conservation of mass, right? We can't destroy mass or make new mass, but we can move a mass, we can change how things are attached to each other. Well, and energy is kind of related to that. You can't destroy it or create new energy, but you can draw energy from a different place or give off energy to another place. And so the first law of thermodynamics says this a little differently. It says the energy of the universe is constant. And in other words, if you take the universe as a whole, any chemical reaction that we're interested in doesn't create or destroy energy in the universe. What it does is it could transfer from that reaction to something else or from something else to that reaction, depending upon the type of reaction that we're going to deal with, okay? There are a couple of different types of energy that we're going to really be interested in. One of them is potential energy. And so for us, potential energy is going to be related to the structure of a compound. In a typical physics course, you might think about potential energy as being related to a position. So like if I have an object at a higher height, right, I'm holding it at this higher height, it has a higher potential energy than at a lower height. And that's because, well, I've done work to lift it up. And so when I drop it, that object at a higher height is going to give off more energy as it falls, right? So there's your potential energy is from a physics standpoint, at least in mechanics for physics. So for us, we're going to be more interested in potential energy from a chemical composition standpoint. Okay, and so from a chemical composition standpoint, really we're going to talk about the energy associated with bonds. Okay, and so one of the things that's going to be useful for us is understanding higher energy versus lower energy. Hold on one second. I'm going to pause our recording here for just a second. Okay, one second. My child is waking up. Okay. Sorry about that, guys. Let's see, where were we? Okay. So when we think about chemical composition, we think about energy, you know, quote unquote, stored in bonds, right? A bond that is a higher energy is a bond that takes more energy to break it. So we're going to find the direction of energy in a chemical reaction is going to be related to the strength of a bond. So when we say it takes more energy to break it, we have to put more energy in order to do so. So it's a more stable bond. And so the potential energy of a bond is going to be something that's useful for us to see. And we'll talk about that as we proceed through this chapter as well. Kinetic energy, we've talked a little bit about kinetic energy already. And when we did that, we were looking at kinetic energy from the standpoint of the energy of a gas, okay? So the energy of a gas, right, was based on the energy of those particles and how those particles are moving. So as the particles of gas move, they have kinetic energy that's related to how fast the particles are moving, which is related to the temperature of the gas, okay? So we touched a little bit on this when we did the root mean squared speed of a gas, okay? Of course, kinetic energy we know is related to temperature because of that root mean squared speed of a gas. Basically, the temperature is just this property that's reflecting how fast those particles are moving, or maybe how much they're vibrating, how much kinetic energy of movement do those particles have, okay? So those are sort of the overall energy aspects of that you may have encountered before when you've talked about physics. And a little bit in our class when we've talked about the speeds of particles of a gas. In this section, one of the things that we're going to be looking for is we're going to be looking specifically at the heat. Okay, so heat is something that's really important for us to measure how much energy can be given off in a given chemical reaction or a process. And heat is just a transfer of energy due to the temperature difference. So if I have two things that are different temperature, right, and they come into contact with each other, they will change temperatures where one of those things gives off energy to the other because of that difference in temperature. For example, if you touch an ice cube, it feels cold to you because the ice cube is taking heat from your finger, which is at a higher temperature, and it's causing that ice cube to melt. Something also related to heat is work. Now, we're not going to deal with work much in here, but work is just the force acting over a distance. So you could say I can do work on an object by lifting it up higher, right? And I'm just lifting that object by a force. In this case, a force could be consider the mass times an acceleration, or the mass times gravity if I'm lifting it up. And I lift it up a certain distance, that does some amount of work to it. And that's sort of the physics sense that we've seen if you've ever had a physics mechanics course. In chemistry, the work that we tend to think about is what's called pressure volume work, and we'll touch more on that, where the pressure, right, is the average force over an area, and the change in volume is, if you think about an area is measured in, say, square meters, and the volume could be measured in cubic meters. And so if you have pressure is force over area, right? So area is in your denominator times a volume, which is measured in cubic meters, right? That actually winds up unit-wise being the same as a force times a distance. And so when we think about pressure volume work, we're talking about a gas that's expanding. When a gas expands, it does work on everything outside of that gas. Okay. Another thing that's important for us is what's, well, it's important to understand, but we won't touch on it as much, is a pathway. So a pathway is how does something get from one place to another? And it turns out that things like work are very much pathway dependent, but a lot of things aren't. So when we say how energy changes, that's what we're talking about. So how does the energy of a system change? Well, in many cases, the way that we get from one place to another, say a chemical reaction, is going to be independent of how it gets there. And for anything that's independent of how it gets there, we consider that to be a state function. And a state function is just a property that depends upon the state of that system, okay? The state of that thing, right? It doesn't matter how you got there, it just, it's a property of where you're at. So if you think about climbing a hill, right? And if you go up a hill, right, that height change is going to be that distance that you would travel, the force being how high you get up there, okay? Or really if you think about potential energy, the height and the mass are going to be things that determine the energy there. Now, it wouldn't matter how you got to that height, you would still have the same amount of energy when you were up there. It wouldn't matter if you went straight up a hill or if you did switchbacks to get up there. The energy that you would have at that higher height is based on where you're at a given time. Okay, so that's what we think of as a state function. It doesn't matter how you get there, it just matters where you're at. Okay. So another thing to think about, just definition-wise, so these are all on our plate before we get into this conversation, is the system and surroundings. So when we think of a system, okay, it's the thing that we're interested in, right? We're interested in, say, a chemical reaction, that's our system. If we're interested in a process, an ice cube melting, that's our system, okay? The surroundings, you can think of the surroundings as just being everything else, okay? So if the ice cube melting is our system, well, the surroundings are, well, where is it pulling the energy from? Is it melting in my hand? My hand is part of the surroundings as well as everything else in the universe, okay? When we look at the internal energy, okay, so we're going to think of internal energy as a delta E for our system. Okay, that internal energy is just a property of the system that can be changed based on where does the work or heat go. Okay, so we're going to look at a system from the standpoint of what are we interested in. The internal energy of a system that is that ice cube that's sitting in our hand if it's melting, right? If the ice cube is the system, it is melting, its energy is going up as it draws heat from my hand, okay? And so the internal energy of that ice cube is going up because of the flow of heat to the ice cube, okay? And so when we think about internal energy, we're really thinking about a system that we're looking at, we're studying, okay? Now, again, when we think about potential energy, we often think of it as based on bonds, and that's this chemical energy, okay? So chemical energy is just the energy that you have associated with making and breaking chemical bonds, and we'll talk more about that a little bit as well, okay? Finally, the last one that we're going to look at here is, the last two things are exothermic and endothermic reactions or processes. So when you have something that is exothermic or endothermic, it's describing a system, in this case, a reaction or a process, and whether that system either gives off energy to the surroundings or whether it absorbs energy from the surroundings. And so that exothermic reaction, if that chemical reaction that takes place is our system, an exothermic reaction is giving off energy to the surroundings. Whereas in an endothermic reaction, the reaction proceeds and it draws energy away from the surroundings as the energy of that, that system goes up, okay? So these are all important things that we'll start to use more frequently as we proceed through the energy discussion of in a sort of very mild way. Again, there is more on this in Chem 102 as you get into thermodynamics and really looking at energy from a standpoint of how, not just how much energy changes, but using energy to predict whether a chemical reaction will occur or not. So those are the definitions that we're going to really start to use much more commonly, much more frequently as we proceed through the chapter. Okay. So we're going to start with the idea of the internal energy of a system. Okay. So when we think about that internal energy of a system, this E, it's the energy that the system has. That system has energy based on how fast those particles are moving around, right? So that has kinetic energy, has potential energy that's associated with, say, the chemical bonds that are between the atoms of the various molecules. But basically, the internal energy of a system is just the sum of all of the particles' energy within a given system. And so in chemistry, we're often interested in changes in energies because the changes in energies are when we have interesting things happen. And so like a chemical reaction occurs, there's going to be a change in energy for that system that we're studying. Okay, so when we think about the internal energy of a system, we're looking at oftentimes the change in energy, right? So we're really oftentimes looking at this delta E, the change in energy, which is really just the final energy minus the initial energy of that system. Or in case of a chemical reaction, the energy of the products minus the energy of the reactants. And so you can get those energies based on the chemical bonds that are between the particles. Okay. Now, there are a couple ways that the internal energy of a system can change. Okay, so if there's energy that's released to the surroundings, all right, so to the surroundings says that the final energy will be less than the initial energy. Remember, when we're looking at the energy, we're looking at the energy of the system, right? Okay, so when we do that, we're looking at the energy of the system. Now, the other way that the internal energy of a system can be changed is when that system gets energy from the surroundings. In that case, the final energy is going to be higher than the initial energy. And you can think about this to some degree on an energy diagram. Okay, and this is something we're going to see more and more. Okay, so an energy diagram is just, you can say there's an energy axis, and if there's an x-axis, it's sort of arbitrary, but we can say, well, if we have a final energy that's greater than the initial energy, well, then you can say, well, this system is going from a lower energy to a higher energy. So that delta E will be positive, will be greater than 0. So this would be, this is one way that directionally the internal energy of a system can change, okay? And so when we think about energy being transferred to or from a system, understanding how it's transferred to or from a system is important. And the most important for us that we're going to see is going to be the heat. And we're going to talk about sort of why this idea of heat, right? Or the thermal energy, right? Energy of the motion of those particles is going to be the most important. And so heat, again, that's energy that transfers based on a temperature difference between two things, say the system and the surroundings. The other way is through work. So if, for example, a gas expands, it does work on the surroundings, and it pushes the surroundings with some amount of force to do a small amount of work on the surroundings, okay? And so being that the energy change is related to both the heat and the work, well, then we can say that the internal energy of a system is going to be equal to the sum of the heat plus the work, okay? In both cases, heat and work are ways in which that energy is transferred. Okay, so work. Okay, so when we think about work, right, so the two most important types of work are electrical work, which we talk about charged particles moving. So these electrons moving through a piece of wire, they have mass, they have some force has to be applied to them to get them to move. So the electrons work is being done on electrons as they move through a wire, okay? Again, that's something you'll talk about more in Chem 102 in electrochemistry when you start to see really processes that get driven by electrical energy, okay? The other type that we're really interested in here is, and we're not going to touch on this a ton, and we're going to see why, but mechanical work, so done when the volume of a system changes. Try that again. So yeah. So when the volume, too fast. There we go. When the volume of a system, sorry guys, having a little trouble. Got a new pen today, so I'm just getting used to it a little bit more. Right, so when the volume of that system changes, right, in the presence of a constant external pressure. So in our example over here on the right, we have a piston in a cylinder. And so inside the cylinder, we've got some sort of a gas. Okay, and that gas has a pressure inside of it that's because the cylinder or the piston can move freely in the cylinder up or down, right? The pressure inside the container is going to be the same as the pressure outside, right? This is an example of a flexible container. And so if a gas does work on the surroundings, the piston is going to move up, right? But in this particular example, if the surroundings do work on the gas inside the container, right, the volume of the gas is going to decrease. And so when we think about the work on the system, right, the work on the system is based on, so this negative P delta V, right? So this negative P delta V, and the negative here, right, this little negative sign comes from the idea that as the volume of the system goes up, the work of that system is going to go down, because in that case, you're doing work on the surroundings, okay? So the work associated with the surroundings is going to go up, okay, as the volume of the system goes up, okay? And so whenever we look at a change in something, right, change in volume, it's just the final volume minus the initial volume to do that. Now, in a lot of the chemical reactions that take place in the gas phase, the gas can expand or contract, assuming it's a chemical reaction that's at a constant pressure. And so that's something that you can take account of in gas chemistry. A lot of the time, though, we're not going to be taking account of the work, and there's a reason for doing this. Okay, and so I'm going to introduce now the idea of what's called enthalpy. Okay, so enthalpy, okay, is an important thing that we think about. We're going to talk about what it is, but basically, it's a thermodynamic variable. Okay, and so it's defined as, so its actual definition is it's the internal energy of a system plus the product of pressure and volume. Okay, so here we say E plus PV, but for us, we're never really interested in the actual enthalpy, the specific enthalpy of something. What we're interested in is the change in enthalpy. Okay, so the change in that internal energy is going to tell us something about the change in energy of a given chemical reaction. And so when you get the change in internal energy, or excuse me, the change in enthalpy, right, this delta H, that's more useful to us than just the enthalpy of something, because it takes into account chemical reactions that occur. And so that's going to be the change in energy plus the plus P delta V, or minus the work associated with that system. So if we substitute that in, the minus P delta V here, then you can, and you kind of rearrange this equation, you can set this equation up for the change in internal energy of the system on the whole, where that is going to be equal to, so Q, or the heat, minus P delta V, okay? So in this case, if you look at this rearrangement, excuse me, actually I should put it this way. If we look at this equation that we saw before, where the change in energy of a system is equal to Q plus W, right, which is equal to Q minus P delta V, and you rearrange that such that you get Q is equal to the internal energy change in the system plus P delta V, right, that's going to be the change in enthalpy of the system. Okay, so Q, the heat, is related directly to the enthalpy. And this is something that works well for us in most situations. So when we talk about enthalpy, essentially for enthalpy, right, we're going to consider it to be it's usually the same as the heat, at least for what we do. Okay. So when we talk about heat and when we talk about a change in enthalpy, right, those two things are going to be somewhat interchangeable. And so there's a reason why we can do that. And oftentimes actually, so the heat and enthalpy are the same thing. But something we're also going to find is oftentimes, should we get into this on this side? Okay, so oftentimes another thing we'll think about is the change in energy of a system is going to often be very close to the heat or the change in enthalpy. And the reason we can do that in many cases is basically if we think about chemical reactions in aqueous solutions, the delta V for an aqueous solution where a reaction occurs, that delta V is going to be equal to 0. So in one case, if we think about a chemical reaction that takes place in water, the change in volume is 0, thus the work term falls out. Okay? And so that's going to be an important thing for us. Okay? Most of the time, we're going to be able to deal with this, with that. Another thing, though, is in general, the work aspect of this is going to be much smaller than the heat. Okay? In many, many cases. Excuse me. Well, yeah, so much smaller than, that's not the one I wanted. Let me do that. Much smaller than the delta E. So I'm trying to think my way through using this new pen, and I guess my brain can only function so many ways. Okay. Get that there. Ah. Okay. So if we look at the work compared to the delta E, it's much, much smaller than delta E. Is that where I'm at? Yeah. And so when that delta E is so big compared to the work, essentially the change in internal energy of the system and the enthalpy, they're about the same. So a small change in work or a small amount of work doesn't change the energy particularly much, right? And that's for many reactions. And even if we're talking about gases, that value, the P delta V, is small for gases because that work that's done it tends to be very small compared to the energy change of the products and the reactants in the chemical reaction, even in the gas phase. So we tend to think about energy and enthalpy and heat all kind of interchangeable to some degree. And they're not exactly, but they're close enough for many of the models that we use. Okay, so the next part of this particular chapter is looking at calorimetry. So calorimetry, we would have had a lab in calorimetry where we actually measured heat using what's called a calorimeter, okay? So the calorimeters that are out there, there's a couple different types. And we're going to do, some of our reactions are going to be based on some calorimetry work. But a calorimeter, right, is an experiment or a device that's used in calorimetry to measure heat or to measure energy changes of a system. And oftentimes the way we can look at this is when we measure the energy change of a system, we're doing so by measuring the surroundings. So one of the types of calorimeters that's out there, okay, is what's known as a coffee cup calorimeter. There are two main calorimeters or types of calorimeters that are out there. So the coffee cup calorimeter is sort of what you see here. Okay, so that calorimeter consists of a few different things. One is, in this case, if you're actually using coffee cups in a coffee cup calorimeter, it's those styrofoam cups are good insulators, okay? And that's sort of a key to this, right? The styrofoam cup is good at insulating, okay? The insulation, right, is just saying that energy doesn't transfer out of the coffee cup very well, right? So an insulator right? It resists the transfer in heat. Okay. And so that coffee cup calorimeter has those styrofoam cups to stop the heat from getting in or out of the calorimeter to the surroundings, to say the air around outside. Inside the container in there, you'd have some sort of a reaction or a process that occurs. You could say the chemical reaction, an acid-base reaction occurs in there, and that acid-base reaction is going to occur between an acid and a base. And while that acid-base reaction occurs, you're measuring the temperature of the water. Okay, so you have the reaction mixture that has, say, reactants and water. And so you can measure the temperature of the water to see how much energy is given off by the reactants in the reaction. Of course, this is covered up and there's a stirrer, so you can help facilitate the reaction and keep it separated from the environment. And your thermometer is the thing that measures the temperature. So that's a coffee cup calorimeter. That's sort of the most common that we use, at least in a general chemistry course. Okay. The other type of a calorimeter is what you see down on the bottom, at least a makeup of it, a mock-up of it, is a bomb calorimeter. So a bomb calorimeter has a similar setup. It's still in an insulated container overall, but the reaction that you're interested in takes place in this little bomb. It's a small volume, okay, down here, right? There's a small volume inside that container. You would have a sample. That sample would be something, something along the lines of maybe you want to do a combustion reaction with something. So in a bomb calorimeter, the container stays the same size, so the pressure in the container can change. So you'd fill that container with, say, oxygen and whatever you want to combust. There'd be some wires in there. You can sort of see these you can see these wires over here, right? Those would be what spark the combustion. And since it's in a high oxygen environment, the reaction takes place in here, and you would measure the temperature change of the water, which is in this insulated container out here, right? So you have a thermometer to measure the change in temperature of the water based on the chemical reaction inside the container. And the big difference between bomb calorimetry and coffee cup calorimetry is that bomb calorimetry is a constant volume, okay? So I think bomb calorimetry, that's constant volume calorimetry, whereas coffee cup calorimetry, something that's more useful for us in general chemistry, is constant pressure. And the reason it's constant pressure is if you think about the cover on top of the coffee cup, that cover on the coffee cup is porous to air, so air can move in and out of it. So it's always at, say, room pressure. Whereas in a bomb calorimeter, it's in this set volume, and this has to be a very strong container because you're literally blowing something up inside that container. That's why it's called a bomb calorimeter. And a bomb calorimeter is really good at measuring heat of combustion. For example, if you wanted to see how many calories there were in a given food, you could take a little piece of food in there, set it in, connect it to the wires, have the oxygen-rich environment, spark it, and that food would combust and give off the energy associated with that food. So you could say, take a little piece of cookie, find out how many calories there are in a cookie by doing bomb calorimetry. Okay. Many chemical reactions that we deal with, though, take place in aqueous solutions, and so we're interested in something more like a coffee cup calorimetry experiment, where we can measure the temperature change of the water in that coffee cup. Okay. And so when it comes to calorimetry, we're going to be doing some examples, especially tomorrow in calorimetry. And those examples are going to deal with these other properties. And so the last thing that we're going to look at here is, well, how do we measure how much energy changes? And the amount of energy that changes is going to be based on the heat capacity of a substance. Now, there's a couple different versions of heat capacity, okay? Now, these different versions are used for different things. just in general, a heat capacity of an object, which is abbreviated with a capital C, right? So here's our capital C. The heat capacity of an object is the heat required to raise the temperature, right? So the heat required to raise the temperature of, in this case, an object by 1 degree Celsius. And so that's the key here. It's the object itself. So if I have a watch, that has a heat capacity associated with all of the components of that watch. The watch itself will go up by 1 degree based on its heat capacity, which is just the heat absorbed by that watch at a constant pressure, and divided by the temperature change of that watch or that object. Okay, and I pick a watch because it's full of all these different components that may have individual heat capacities that are different, right? If I have a watch that's made of plastic and maybe leather for the band, and that each of the gears has a different heat capacity associated with that metal, then all of this together gives us that object that has its heat capacity. Whereas the specific heat capacity is if I have a substance, one substance, not a combination of things, that substance, say water, for example, that water, its temperature will change depending upon how much of it you have. And so the next type of heat capacity, and sort of one of the most important heat capacities that we will look at, is going to be the specific heat capacity. So the specific heat capacity, C subscript S, and this is a lowercase c, is the amount of heat, okay, so the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So now we're saying, oh, okay, if we have 1 gram, it will go up by 1 degree Celsius with a certain amount of heat added, okay? And so that's going to be the heat absorbed at a constant pressure by that sample, if you will, of, say, water or maybe a piece of metal, divided by the mass of that sample and the change in temperature associated with it. So in other words, an amount of heat will raise the temperature of something. The amount that raises the temperature is dependent upon the heat capacity of that substance and how much of it that you have, okay? Related to the specific heat capacity is the molar heat capacity, okay? So C sub M instead of C sub S. And that's the heat required to raise the temperature of 1 mole of a substance. So the specific heat capacity and the molar heat capacity are related to each other just based on the molar mass of that substance, okay? And just keep in mind, anytime we have a change in temperature, change in anything, right, it's the final minus the initial conditions for that substance. So when you look at delta T in terms of degrees Celsius, a delta T in terms of degrees Celsius will be the same as the delta T in terms of Kelvin, because this is a final minus initial, right? So if I look at, say, boiling water, right? So H2O, back to that. Okay, so if I look at water boiling compared to water freezing, right? If I look at those two temperatures, water boils at 100 degrees Celsius and it freezes at 0 degrees Celsius. So the delta T there would be 100 degrees Celsius. But we also know that it's related based on the absolute zero. So water would boil at 373 Kelvin and freeze at 273 Kelvin. And so again, we would have 100 Kelvin difference there. So you can see that the delta T, whether it's in degrees Celsius or in Kelvin, it doesn't really matter. They scale the same, so the changes are going to be at the same rate, okay? And so what we'll do now is we'll stop there for today and see that, well, once we have this idea of what a calorimeter is and that a calorimeter can measure the heat change, what we'll do tomorrow is we'll take that and we'll take our heat capacities and put our heat capacities to use to measure, say, changes in the heat of a substance, how these are related when you have two objects that are in contact with each other, And so we'll do that for initially for just a process, the transfer of heat. We can measure that transfer of heat. And then we'll start to think about measuring chemical reactions as well. Okay, and with that, yeah, Amir.
Just a small question about the bomb calorimeter. I just wanted to know, so it does actually happen in a dry environment in comparison of the coffee cup
Yeah,
calorimeter.
that's right.
So the other difference is it's in a dry environment all the time.
Yes. Yeah. So the actual chemical reaction that takes place occurs inside this calorimeter. So you want it to be dry. That's why like combustion is done in there. You actually produce water in combustion, right? CO2 and H2O are the products of combustion. But initially you want it to be largely very dry so that when you spark it, it reacts automatically. Yeah.
Thank you.
Very quickly. Yeah. Okay. Any other questions? All right, then we will pause our recording or stop our recording there.